Hey everyone, in this video we're going to be talking about subspaces of Rn. Okay, so the idea here is it's a bit theoretical, but hopefully this will make sense to you after we go through it. So here's a definition of what we're talking about. We're defining what's called a subspace of Rn, and it's any set, so think of a set like a collection. In our case, it's going to be containing vectors. Any set in Rn that has the following three properties. So basically, we have to verify these three properties. If all three of these are true, then by definition, we can call that set a subspace. And so property 1, the 0 vector has to be in that set. Property 2, for every 2 vectors in that set, when you add them, that result has to be in the set. And then property 3, for any vector in the set and a scalar, when you multiply that vector by a scalar, that result has to also be in the set. Okay? And so what we say is that the subspace is closed under addition and scalar multiplication. That's for properties 2 and 3. Okay, so when you take two things and you add them, and that result is in your same set, then that's considered closed under addition. If you take something in the set, you multiply it by a scalar, and the result is still in the set, it's closed under scalar multiplication. We're going to talk about our vectors, but just so you are aware, think of this with numbers. The real numbers are closed under addition and multiplication. So just for example, let's just say we had 1 plus 2. Those are both real numbers. If you add them up, you get 3, which is still a real number. Let's say you had 5, let's say u is 5. So 5 times 7. Then 35 is still a real number. So is 5 and 7. So those are closed. The real numbers are closed under addition and scalar multiplication, just to help you wrap your head around it. All right, so here's our example. Verify that if v1 and v2 are vectors in Rn, and h our set, we're calling h the set which equals the span of those two vectors, then h, by definition, is a subspace of Rn. So real quick, let me remind you, span of vectors is all the linear combination of those two vectors. In this case, it's two vectors because we're only talking about v1 and v2. So we're going to verify all three of our properties. So the first one, the 0 vector is in H. And here's why. 0, the 0 vector, is the same as 0 times v1 plus 0 times v2. And because you can write the 0 vector as a linear combination of v1 and v2, by definition, that's the span of v1 and v2. And so we say that 0, this symbol means belongs to or is an element of. So 0 is an element of H. All right, so that's property 1 verified. Property 2, H is closed under addition, and here's why. So let's just consider two arbitrary vectors, u and v. Those are going to be in our space or set H. And then we're going to notice that when we add them, the result is also going to stay in H. Okay, so we're just saying in general, let u be c1 times v1 plus c2 times v2, and v is very similar. Okay, so notice u is a linear combination of vectors v1 and v2, and then v is a linear combination of vectors v1 and v2. Now let's see what happens when we add them. So if we add u plus v, and then we just do a little bit of combining, notice what we have. We have two scalars being added times v1 plus two scalars being added times v2. And so that is a linear combination of v1 and v2. So remember, any linear combination of v1 and v2 is by definition the span of v1 and v2, and that's what we're calling h. So the addition, the sum of our two vectors, belongs to H, so it's closed under addition. Okay, last property to verify for this one. H is in fact also closed under scalar multiplication. Let's see why. So just consider any scalar, we'll call it C, and then any vector v in our set H, and then notice that when we multiply C times v, we're going to stay in H. Okay, so here's our vector v. If we multiply it by some scalar, notice what we can do. We can just do a little regrouping. And so it looks like c times d times our vector v1 plus c times d2 times our vector v2. So this by definition is a linear combination of v1 and v2, which that means is in the span of v1 and v2, which equals h. So c times v stays in h. So we verified all three properties just to show that this set h, defined as a span of these two vectors, is in fact, by definition, we can call it a subspace. So it's a set of vectors, but now we can give it the title subspace because it satisfies those three properties. All right, so here's a visual. We talked about the span before in the past, but the example we just talked about, this is a way to visualize that subspace for two vectors. It just looks like this plane in two dimensions. Okay, any linear combination of v1 and v2. Okay, so again, in the past we've talked about this, but let me just sort of mention how you can get combinations. Just for example, we could say something like 3v1, which would get us up here, plus 1v2, which would put us here. So that exists in our plane, which is a visual for our subspace. Okay, that vector 3v1 plus v2 would be this one right here, from the origin to right here. Okay, so here's some facts for us. The span of our vectors v1, v2, and so on all the way to vp, we call it the subspace spanned by, or you could say generated by, those vectors. Okay, and then another fact, Rn is a subspace of itself. And then last fact here, the zero subspace contains only the zero vector. So 0 is still considered a subspace, but the only thing in it is a zero vector. All right, now we're going to move on and relate what we just talked about to what we've been learning about, which is matrices. So we're going to talk about first the column space of a matrix. So here's our definition. So we just learned the definition of a subspace. Now we're going to relate that to our matrices that we've been learning. And so the definition of a column space of a matrix A, it's denoted COLA, so col A, or column space of A. And it's basically just all linear combinations of the columns of A. So it's a set. Notice that it is a set. So it's like a collection. And it's just a collection of all the linear combinations of the columns of your matrix. And so you might be thinking, what's the difference between our span? Well, it's very, very much the same in most situations. So if A is a matrix where all of the columns of your matrix are in Rn, then the column space of A is the same thing as the span of the vectors A1, A2, and so on. All right, so let's take a look at this example. So this example shows that the column space of an M by N matrix is in fact a subspace of Rn. So we're just relating, just so you're aware, we're relating column space to what we just talked about, which was subspaces. So here's our example. Matrix A is this 3 by 3, and we have a vector B. And so what we want to know is this vector B in the column space of A. Okay, so here's how we solve this. The vector B is a linear combination of the columns of A, our matrix, if and only if it can be written as A times X for some vector X. So that is, if and only if this equation AX equals B has a solution. So we've been doing this. We're just now relating new things to what we've been doing in the past. We solved matrix equations before, so we're just doing that still and talking about it in a little bit more detail. All right, so we're going to row reduce our augmented matrix where the left 3 columns came from A and the right column was B. Okay, and so just do your row reduction. So after a couple of steps, we're going to get zeros underneath our first pivot. And just so you know, if you want to verify, that came from just saying 4 times row 1 plus row 2 to get this new row 2. And then our new row 3 is from doing 3 times row 1 plus row 3. Okay, and then we want to keep reducing. And if you just try a little bit more, actually just one more step, you'll find out that the bottom row becomes all zeros. So if we do row 2 plus negative 3 times row 3, then the whole bottom row becomes all zeros. But we know what this means. This means there's infinitely many solutions. And so how does that relate to what the question was? It means that the equation, our matrix equation, is consistent, and therefore B is in fact in the column space of A. Okay, so putting it all together, we're just talking about what we've seen in the past a little differently. We've solved matrix equations before. We've row-reduced augmented matrices. And so because this equation is consistent, it's saying that B is a linear combination. It can be written as a linear combination of the columns of A. And therefore, by definition of column space, B is in the column space of A. So things we've done before, but just talking about them in a little bit more detail now. All right, so now let's talk about what's called the null space of a matrix. And so the null space of a matrix A, we write it as NULA, so you just read that null of A, or null space of A, is just a set, so another set or collection. And this is one where all the solutions of the homogeneous equation, AX equals 0, belong to that set. And so we have a theorem that corresponds with this. And so the null space of an M by N matrix A is, by definition, a subspace. So more definitions for us. We learned about subspace and column space. Now we learn about null space. And null space is just the set or collection of all of our solutions to this equation when we have AX equals 0 instead of like the last example where it equaled a vector B. And so this null space is a subspace of Rn. Another way to say this theorem is that the set of all solutions of a system of AX equals 0, of M homogeneous linear equations, so the set of all solutions to these M linear equations, where there's N unknowns, so like N variables, is a subspace of Rn. So let's just do a quick walkthrough of the proof of this theorem. So we're claiming that the null space of this matrix is in fact a subspace. So remember, to prove that something's a subspace, we need to show our three properties hold. And so we'll just mention it real quick. 0 is in the null space. It's in the set because A times 0 is still 0. Okay, so the 0 vector is in the null space of A. So that's property 1. Property 2. So to show that the null of A satisfies the other two properties, let's say that U and V already belong to the null space, to that set. So suppose that A times U equals 0, so it satisfies our homogeneous equation, and so does A times V. So then, by our property of matrix multiplication, which we've multiplied matrices in the past, we have that A times the sum of U plus V can be written as A times U plus A times V. Since they both equal 0, then the result is 0. So this satisfies our equation, A times U plus V equals 0. And so therefore it is satisfying part 2 of our subspace requirement. Then the last one was our scalar multiplication. So for some scalar C, A times the vector C times U, and then you can change the C, bring it out, like basically just commute these. So C times A times U, and then we have that this is the same thing as, oh, little typo here, no X. So this is the same thing as C times 0 equals 0, which shows that it satisfies our equation. So the scalar multiplication is in the null space as well. So just a quick proof of that theorem, that null space is in fact by definition a subspace. Okay, next definition, and this will be the last definition and then we'll go through an example, but we learned about our subspace, column space, null space, and now a basis. So a basis is what we call a subspace of Rn, where we have linearly independent vectors in the set that span H. Okay, so a basis for a subspace is a linearly independent set in H that also spans H. So an example of a basis would be the columns of an invertible n by n matrix. So if you have an invertible matrix, remember that just means it has an inverse, then the columns of that matrix actually by definition form a basis for all of Rn, and that's because they're linearly independent, each column, and the columns span Rn. And this is by the invertible matrix theorem. So let me show you that theorem real quick. And so here's the invertible matrix theorem. We talked about invertible matrices in the past, but this will be a good theorem just to have available for reference because it has a lot of parts to it. So all of these are basically true together or they're all false together. And so what we just did for that last example was we used actually fact E and H. So if we put that together with A, so if A is an invertible matrix, then the columns of A form a linearly independent set, and those same columns span Rn. So we use both facts E and H to claim that A, an invertible matrix of size n by n, is in fact a basis for Rn. All right, now one particularly useful matrix or basis is going to be what we call our standard basis, and so it's the identity matrix. And so we've seen this before. We denote the columns of any identity matrix with E sub 1, E sub 2, and so on, depending on its size. And so the set containing these columns or vectors, we call that by definition the standard basis for Rn. So for example, the standard basis for R3, think of it like for 3 dimensions, is the set containing E1, E2, E3, where E1 is just 1 in the top position, 0, 0 below. E2 has 1 in the middle position. E3 has 1 in the bottom position. If you put this together, notice you would get a 3 by 3 identity matrix. And all 3 of these vectors, these span 3-dimensional space. Okay, you can create all of 3-dimensional space as a linear combination of these 3 vectors. So that is an example of a standard basis. Okay, so the last thing is to find a basis. So here's a quick theorem. The pivot columns of a matrix A actually form a basis for the column space of A. All right, so now let's find a basis for the null space of the matrix A. Okay, so notice what we're asked to find. We're asked to find a basis, which is a set of linearly independent columns or vectors. And this is for the null space. So remember, the null space is the set of solutions that satisfy that homogeneous equation. So we have to know what these definitions are meaning for us to be able to even attempt this question. So just make sure that we're aware of that. And so the first thing we're going to do is set this up as an augmented matrix. Okay, so here's our augmented matrix with zeros in our answer column. And we're just going to go through row reducing this as much as we can. All right, so the first equivalent matrix I have here is just from swapping rows 1 and 2. Then the next one here, feel free to pause this as I go through it if you want to try to work it out first before I show you. But this next version is from doing 3 times row 1 plus row 2. Okay, then take a look where we're going next. We're trying to get zeros in this pivot column over here. And that's from negative 2 times row 1 plus row 3. Okay, let's keep going. So here's where we're at. And next we are going to, notice, do 1/5 times row 2. One more step. Notice that rows 2 and 3 are the same. So if we just do negative 1 row 2 plus row 3, we get all zeros in row 3. And so there's our results. And actually one more step after that, let's go ahead and turn this 2 into a 0, since this is a pivot position right here. So that's just from negative 2 row 2 plus row 1. And so what we have here is our equivalent matrix to our augmented matrix A and 0. And then if we write out these equations that these rows represent, notice what we have. Okay, and then the way we're going to write this, remember, if any variables are free, which in this case there are free variables, we're going to write our basic variables in terms of those ones. So notice we have a pivot in column 1, which means x1 is basic. We have a pivot in column 3, so x3 is basic. But then x2, there's no pivot. x4 and x5, there's no pivot. So those are the free variables. All right, and so we have x1 written in terms of the free variables, x3 written in terms of the free variables, and then the other three are free. You could say in words that they're free, or you can say that they equal themselves. So you could say something like x2 equals x2, x4 equals x4, x5 equals x5. So you just solve these equations up here for x1 and x3. That's where these came from. Okay, so putting this all together, look what we end up with. So if we just take our general solution that we just came up with from our row reduction of our matrix, we have the vector x containing x1 through 5. And then notice what we have here. Notice all I have written. x1 equals this right here. 2x2 plus x4 minus 3x5, which was equation 1. x2 was free, so it equals itself. x3 equals what we got up here, negative 2x4 plus 2x5. And then x4 equals itself, and x5 equals itself because they're free. And so what you're going to do here is sort of think of it just like factoring. So x2, think of it like factoring it out from this vector here. And so it says x2 times 2. And then in the next column, there's 1 x2. And then in the next column, there's no x2s, so that's 0. Third and fourth and fifth column as well, no x2s, so all zeros. If you multiply this back out, 2x2, and then if you move on to the next one over here, plus 1x4, minus 3x5, you're going to get row 1 here. Okay, so you do that for x4 as well. Notice just real quick, in row 1, there's 1x4, that's why there's a 1 here. In row 2, there was no x4s, so that's why there's a 0. Row 3, there was a negative 2x4. Row 4 had 1x4, and row 5 had none. It's very similar. Oh, I forgot a plus sign. It's very similar right over here to the last one for x5. And so what this is telling us is if we think of these three right here as vectors, I'm calling them u, v, and w. Then we can say that the null space of A coincides with the set of all linear combinations of these vectors, u, v, and w. And therefore, the set containing those vectors, this one here, and this one here, form a basis for the null space of A. All right, so it's a little lengthy in this one, particularly for finding the basis of a null space. We're going to do one more example where we find the basis of a column space, which is actually less work than for the null space. All right, so here's our same theorem. We're going to use it this time, and this was the pivot columns of a matrix form a basis for the column space. So we're just going to quickly go through this. If I have to find a basis for the column space of this matrix, I skipped all the steps, but this was what I get from row reducing it. And notice where we have pivots. We have a pivot in column 1, a pivot in column 2, and a pivot in column 5. And according to this theorem, the pivot columns form the basis of the column space. And so if I just denote the columns as A1 through 5, then the pivot columns are column 1, 2, and 5. Okay, so just repeating that here. And then the set containing column 1, 2, and 5 form a basis for the column space. So quick note on this one. Notice where I took the columns from. Even though I row reduced the matrix, I did not take them from the row reduced one. I actually take them from the original. So I row reduced my matrix to figure out where the pivots are. From here I could tell it's column 1, column 2, and column 5. And then my answer, I go back to the original and say, well, here's column 1, here's column 2, here's column 5. And those vectors, the span of those vectors basically creates the column space or generates the column space of A, and therefore it's a basis. Okay, so that's it for this one. Thanks for watching.